Hello everyone and welcome to today's webinar in the CERDP and ESTCP webinar series. My name is Jennifer Nyman. I'm a Senior Engineer at GSN Tech Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of CERDP and ESTCP by Dr. Andrea Leeson, followed by a listing of the upcoming webinars in CERDP and ESTCP's webinar series. Following Andrea's opening remarks, we will transition to the technical portion of the webinar. Today's webinar features two speakers who will discuss sustainable pyrotechnics. First, Dr. Eric MacLeish will discuss removal of perchlorate oxidizers from red and green emitting pyrotechnic flares. This will be followed by a brief question and answer session that will be specific to that presentation. Second, Dr. Moretti will discuss sustainable incendiary projectiles, followed by a second brief question and answer session. We will conclude the webinar with an interactive question and answer session, including both of our speakers. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the question and answer period to submit the questions. In fact, we encourage you to submit questions in advance of the sessions. With over 100 attendees on today's call, it is logistically challenging to open all of the lines for oral questions. Therefore, the phone lines will remain listen only throughout the presentation. We have provided a few suggestions on this slide in the event that you experience any difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference call line. However, if you do continue to have problems, please submit a chat in the lower left-hand chat box, and the CERDP and ESTCP support office will address any of those questions. With that, I would like to introduce Dr. Andrea Leeson. She's the Deputy Director of CERDP and ESTCP, as well as the Program Manager for Environmental Restoration. Andrea has been with CERDP and ESTCP since 2001. Prior to that, she was a research scientist at Battelle Memorial Institute. Andrea?
Thank you, Jennifer. I'm happy to welcome everyone to CERDP and ESTCP's webinar today. I'd first like to give you a little overview of our programs. CERDP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. CERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. CERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under CERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERDP and ESTCP are complementary programs, with much of CERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are 4 program areas in CERDP, 5 in ESTCP. The Energy and Water Program area is only in ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and climate change, and weapons system and platforms, are CERDP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Weapons System and Platforms program area. Weapons System and Platforms has essentially 5 main areas of research: surface engineering and structural materials, energetic materials and munitions, noise and emissions, waste reduction and treatment in DoD operations, and lead-free electronics. Our webinar series will be highlighting research and demonstration efforts from each of the 5 program areas. As you can see, our webinars will cover a broad range of topics, with upcoming topics covering characterization and remediation in fractured rock environments, to munitions response and land-based program closeout, to emerging contaminants. The next webinar, based on research and demonstrations conducted under the Weapons Systems and Platforms program area, will be on October 1st and will address hexavalent chrome elimination from hard chrome surface finishing. You can find more information about upcoming webinars on the CERDIP and ESTCP website. Registration is actually now live for the webinar on characterization and remediation of fractured rock on August 20th. I hope you enjoy the webinar today. Jennifer?
Thanks, Andrea. And now it's my pleasure to introduce our first speaker, Dr. Eric MacLeish. He's a member of the Pyrotechnics Operations Branch at the Naval Surface Warfare Center and Crane Division, which has been tasked with the removal of perchlorate oxidizers for naval pyrotechnic formulations over the past 15 years. Dr. MacLeish's research focuses on the development of novel pyrotechnic compositions, product improvement of in-service units, and environmentally friendly reformulation of in-service pyrotechnic compositions. Dr. MacLeish received his PhD from Purdue University, where he studied energetic material combustion. Eric?
Thank you very much for the introduction. As I was introduced, my name is Dr. Eric MacLeish. I'm here with Ms. Christina Yamamoto from the Naval Surface Warfare Center, Crane, in Crane, Indiana. And I'm happy to participate in today's CERP and ESTCP webinar series, and we'll be trying to discuss several projects we've had over the past 13 years on the removal of perchlorate oxidizers from red and green light emitting pyrotechnic flares. So I'll give you a brief outline of what my discussion is going to be about today. I'm first going to motivate the need to replace these perchlorates from in-service units. And the short version of that is that we have a lot of regulatory drivers that make it prudent to remove these oxidizers from in-service formulations. I'm going to discuss the effect of these regulations on various DoD operations, specifically pyrotechnic units. And then I'm going to move on to our reformulation strategies, how we plan to take these perchlorate oxidizers out of these formulations, and then go unit by unit through some of our various in-service units that we've targeted, talk about how we did it, a view of some of the lessons learned in those projects, their successes, and ongoing work. So to start off, I want to what the concerns with the perchlorates are. I want to first discuss who uses perchlorates. And if you look at the chart on the lower left-hand side, overall the DoD, NASA, and defense-related industries use a large portion of perchlorates across the entire United States. In DoD, mostly this is in rocket motors using ammonium perchlorate and pyrotechnics using potassium perchlorate. And the reason this has been identified by the EPA as a health issue is that the perchlorate ion can block iodine uptake in humans. So specifically, if ingested, perchlorates can cause these types of health issues in pregnant women and children. The specific concern that goes with DoD facilities, and I'm just kind of transitioning to my next slide, my next point that I'm making is that because the DoD makes so many of these items, as shown by this pie chart, we also test these, and all these testing sites will have remnants of these tested materials. So the perchlorates tend to be very water soluble, so they're not just going to stay at the testing grounds. Rain and moisture can cause them to solubilize into water and move. They have a tendency to get into groundwater. So EPA has identified this as an issue, and as I'll show you on the next slide, there's a lot of testing facilities where we've seen very, very high perchlorate levels being documented. The regulatory levels as set by the EPA is currently set at 15 parts per billion across the country, but some states have taken it on to lower that level to 1 part per billion. And in 2010, I have this is the last version I was able to get. 16 different DoD sites had such high levels of chlorates that various stages of remediation were in effect, which means we have to go in there and we have to remove the perchlorate contamination that has already taken place. And the point I want to make right here is that perchlorates are, this contamination is very expensive to clean up once these levels have been seen. You can see things over 2 million parts per billion at various facilities across the United States using various services. And when this is specifically become of interest in pyrotechnic related items. The first time in 1997, we actually had to stop training with a flashbang simulator at Camp Edwards due to perchlorate contamination concerns. This M116 had perchlorate items in it, and we actually had to stop training, which brings troop readiness into, becomes an issue. In 2000, the same place, Camp Edwards, was closed due to these same perchlorate concerns. And this is like the first time it really became into the pyrotechnics arena that were actually directly affecting DoD operations with these EPA-based regulations. Over this period of time, being in the 90s and early 2000s, CERP was funded and has continued to fund numerous projects to address these DoD perchlorate issues. Some of the early projects were biological impact assessment, evaluation of mitigation techniques, including cost assessments, and it turned out to be, it's very, very expensive to have to go into the groundwater and try to clean up this contamination once already taken place. So the more forward-thinking approach, which is going into this project, is not only to clean up the sites that are already contaminated, but to remove perchlorate so that future contamination does not take place. So since 2002, we've been very fortunate to be funded by CERP and ESTCP here at Naval Surface Warfare Center Crane, as well as we've collaborated with the Army Research Development and Engineering Center at Picatinny to be developing a wide range of perchlorate-free pyrotechnics. These have focused on visible flares, smoke signals, delayed compositions, incendiary compositions, all together, but here at SWC Crane we mostly focus on just visible signal flares. Many of these perchlorate-free compositions have been transitioned into service, and I'll be talking about some of those today. So if I had to summarize what we've been working on under these projects over the last 13 years, it's kind of difficult to do, but if I had to say one objective, it would be that we want to develop and implement robust, tunable, perchlorate-free pyrotechnic formulations into as many military colored signal flares as possible. Now, if we're talking about unit-by-unit goals, if we take for instance, I have a picture of Mark 124, the new formulation needs to produce equal or superior performance to the old formulation. We don't want to take a hit in performance just because we're trying to make them more environmentally friendly. And we also want to produce no additional hazardous byproducts. I'm going to talk a little bit at the end of the presentation about what is the definition of hazardous byproducts, but the short story is that is determined by the EPA via regulations, and the regulatory environment is ever changing. Right now we are focused on removing perchlorates, but that could be changing, and that will be a bit of a discussion at the end of my talk. The signals that I'm going to be talking about in this presentation are over a wide range of form factors. We have the relatively moderate size from 20 to 90 grams being the handheld signal flares, which I'll start the presentation with. We have small signal flares being about less than 5 grams, and over 130 grams, so the relatively large signal flares that are going to be implemented in, as submarine smoke and illumination signals. So we're going to try to implement these robust, tunable, perchlorate-free formulations into as many of these different form factors as possible. So to discuss our generic approach to the reformulation strategy, I'm going to first introduce you to some standard formulations that are used to produce green and red light in military flares. You can see we have a magnesium fuel, which is very common, and then we have our energetic potassium perchlorate oxidizer. Potassium perchlorate has traditionally been used because it's stable, it's high energy, has chlorine, has oxygen, has everything you want to make a bright burning flame. And then we have our nitrate salts. So for green flares, we're going to have the barium nitrate. That barium is going to go on and produce our green light. And red flares, you have strontium nitrate, which the strontium will go off and produce the red species, which I'll discuss in a minute. You can have a secondary chlorine donor. The PVC is polyvinyl chloride, and this is going to be as a burn rate modifier and a secondary chlorine source. Lastly, we have our binder. You can have a series of dry and wet binders being used in current in-service units, and I'll discuss unit by unit what was being implemented and our strategy going forward as we're introducing a new binder in these systems. For combustion products, we're introducing magnesium oxide, and then primarily our emitting species are going to be the barium hydroxide, barium chloride for green, strontium hydroxide, strontium chloride for red. So for our new formulations, we're just going to be simply trying to take out the perchlorate, replace that with the nitrate salts that we're already using as the primary oxidizer. When needed, we can use high nitrogen materials, alternate fuels, and we'll be using the PVC as the chlorine source. Those chlorinated emitters tend to be better emitters than the hydroxides. Additionally, we're going to be trying to implement the EPON-Versman binder system into all of our new perchlorate-free formulations. This has advantage over the dry binder system, which I'll discuss specifically later, is that it's more safe. And the laminac luprosol system, which is a similar two-part epoxy that was previously used that had limited commercial availability. So these are our general formulations on the bottom, four-part system. You have your magnesium, your nitrate salts, your chlorine donor being the PVC, and our two-part epoxy. So just to give you a general idea of the mixing procedure, we're going to add our fuel and our binder. This is a very hands-on approach. There's operators that are very involved in this process, are exposed and are directly working with this material. Then we're going to mix it in step 3 for a couple minutes. Up till step 4, we don't actually have a pyrotechnic material. At step 4, we now have the fuel and oxidizer mixed together. And then now we have to be cognizant of safety concerns at this point due to the chemical energy combined in that material. I'll be talking a little bit later about the curing process. This is a two-part epoxy being used as a binder, so there's a curing process that takes a certain amount of time, and actually pressing and processing the candles at a specific point during that curing process is shown to give us the best results. So we actually wanted to let that glue partially cure, or set up as we have to call it, and then we're going to re-sieve it as it's going to become a little clumpy to the glue drying, and then we'll have an optimum time for processing, actually making it into a robust candle with good structural integrity. A really quick note on how we're perceiving color and measuring color. We'll be talking about 4 quantities to discuss the performance requirements of the candle. One is photopic intensity. It's how much visible light the source emits, whether that's measured in candela. How long the candle is actually burning is measured in burn time in seconds. The dominant wavelength and color purity are a way that of documenting what color the flame is as perceived by the human eye. So as you can see on the bottom left, I have a little diagram of a polychromatic light being emitted from flare, and our eye only sees actually one color. It's going to be some combination of these colors, and this is all documented according to the CIE 1931 chromaticity diagram and color matching functions that have all been standardized. So the dominant wavelength is going to represent the perceived monochromatic light equivalent of whatever polychromatic light is being emitted, and the color purity is going to be the tint of the emitted light as a ratio of color to white light. Due to time restrictions, I'm just going to leave that generally described as such. So to get into our actual units, the M126A1 is a hand-launched unit used for signaling troops and aircraft. This is a military unit, so I'll be able to give you the exact specification, or Army unit, so I can give you the exact specifications here. We have a 10,000 candela brightness and a 50-second burn time. This is one of the longer burn items that we have. This is a collaborative effort. We developed and qualified this with Naval Surface Warfare Center Crane and Picatinny as well. We took 2 different approaches and chose the best highest performance composition. RDEC was exploring high nitrogen compositions, which I will not discuss in detail right now. And we went after this more traditional composition, which I described previously, being the magnesium, the strontium nitrate, the PVC, and the epoxy. Major accomplishments is that we did a full systems demonstration with a manufacturer, being Security Signals Inc., and this is actually currently being used in service, which we're very proud of. You can see a function test of this at our current facilities here, and side-by-side comparison of the old and new flare compositions being burnt in our test tunnel. You can see that they're very similar. In partnering with SSI, we went through a process engineering study to actually implement our this new perchlorate-free formulation into their existing processing at the full-scale manufacturing environment. We went through several different techniques, and we started with their traditional processing steps, which I'm going through this flow chart. I'm starting on the right side and moving to the left. Their original processing was to fully cure the composition, so we're going to mix it. We're going to have an epoxy in there. We're going to fully cure it. We're going to press in the candles. We're going to have a second curing step with the fully cured candles, and then we're going to what's called slurry, which means to add the ignition composition to the top of the candles to allow for easy ignition. And we're going to cure a third time. So there's a lot of redundant curing steps going on in this process, and we want to try to eliminate some of those, as well as we found with our new perchlorate-free that was not a favorable end candle. So the best case scenario is if you can just mix it and immediately press it. So that's the next thing we tried. We can move into the left now. We have the uncured composition, and we're going to try this wet pressing technique. And to kind of gloss over this, because of the we're immediately pressing this as soon as we mix it. The composition turned out to be very sticky and was not flowing well. It didn't have desirable viscosity, and we did not make very good candles. We tried several different techniques, and this turned out to not work. So eventually what we ended up doing is we were pressing these partially cured compositions. So if you look at the bottom where I say new method based on process engineering study, you'll find the final method that we chose, where we're going to mix the composition on day 1. We're going to let it set at room temperature overnight, so it's going to partially cure. This epoxy is going to partially set up. We may have to do some seething or something along these lines to increase the processability. But on day 2, we'll press the candles. We'll immediately put the ignition composition on there and cure. And then on day 3, we will have our final candles ready. So in summary, we went to this SSI. We had successfully implemented this material. We have no additional processing time. We started with a 3-day process to make these candles. We ended with a 3-day process. And we saved the cost of having these redundant curing steps. So overall, a very successful implementation, and these are now being used in service. So to move on to our next target was the Mark 124. Mark 124 is a marine smoke and illumination signal. This is a 2-part flare. It is a side-by-side smoke signal for day use and a flare signal for nighttime use. We had previous work not related to the SERP and ESTC projects to remove the perchlorate from the smokes. So with this ESTCP project, removing the perchlorates from the flare unit, we were able to actually take the perchlorates out of this entire Mark 124 unit. And I want to take a quick note to say that this unit is used extensively by the Navy and Coast Guard, and there's an additional not exact duplicate, but a modified unit that's available for civilians. So the big point here is that this is a very widespread used item and has potential large impact by taking perchlorates out. So the major accomplishments is we developed a successful formulation. This formulation was relatively similar to the M126A1. This one was actually developed first, but by developing this robust, tunable formulation that we've developed, we can just tune the ratios, the field oxidizer ratio, to make these different units meet these specific performance requirements. You can see that this unit has a 19-second burn time, and the M126A1 has a 50-second burn time. But because we developed this robust and tunable formulation, we're able to drop these into the different form factors and have a successful unit that meets all of its requirements. So we've completed formulation qualification testing, which verifies that it's safe to be used. We completed system demonstration testing, which I'll talk about on the next slide. And we've identified a program office support to transition this to being used in the service. So we're very, this is not currently being used in service, but we're very excited about transitioning this in the future. The system demonstration we did was at Kemmering Ordnance. And one second. So Mark 124, with the current manufacturing in Kemmering Ordnance, we went there with this different perchlorate-free formulation, and we implemented it using their existing equipment and processes. Using knowledge we gained from the M126A1 process engineering study that I previously discussed, we were able to meet the performance goals very, very rapidly. So we did 2 large manufacturer scale batches. And on our first batch, we made just the candles, and our perchlorate-free candles met the performance specifications. You can see some of the data on the lower right-hand side of this slide that our intensity is roughly 3 times what our target was. This is not the exact specifications. I'm not allowed to release that in this environment, but that was our goal that we were going for, and you can see that we have a lot of trade space available that we're greatly surpassing the intensity requirement. You can see they were hitting just about the burn time we were shooting for, and we're producing a high color purity red flare. So our first batch, we were able to make the candles and show that we can transition this to a new area. In the second batch, we built the full up units, and we once again showed that the candles met all the performance target that we were going after. So to kind of summarize, we met all the specifications we were going after. We have superior intensity to the current target and the current signals. We have quite a bit of trait space available, so if we want to modify the burn time or intensity, we have this documented tunability where we should be able to accommodate that. And we have a near cost equivalent from a perchlorate-free composition to what was previously being used. This is compatible with all of the existing processes and procedures, and the contractor, by switching to this two-part wet binder from the previous dry binder system, being the asphaltum, there were several concerns going into this work. One was that we're going to a curable system that has a finite shelf life. Being the dry binder system, there's no curing process. You can potentially hold on to it for quite some time. And we demonstrated with the two-part epoxy that by changing the ratio of the EPON inversement, that's our binder system, by changing that ratio, we've demonstrated a 6-day shelf life. So you can mix on day 1, you can hold on to it for 6 days, press it on the 6th day into the full-up candles and still have the desired performance that we're looking for. So with a different contractor than previously, we were able to transfer this knowledge and show good mastery of being able to transition these formulations from our facilities to the full-up manufacturer scale. Next target we worked on is the M195. The M195 is functionally identical to the M126A1, except that it's a red light instead of green light. Once again, we had a collaborative effort with ARDEC. They explored their non-traditional flare compositions, as I'm calling them. I'm calling ours as the magnesium, would be barium nitrate, PVC epoxy would be our traditional. They went after ceramic field and high nitrogen materials, and in this case, the non-traditional ceramic high nitrogen formulation was chosen to move on to the systems demonstration. I'm not going to discuss this in excess here, but this is a joint effort between the ESTCP and Army EQT program, and system demonstration is ongoing, and they're doing a pilot scale, supposed to be this month, I believe. So very happy with this unit as well. Now going from the handheld signals, which is the moderately sized candles, from 20 to 90 gram signals, we're going to the relatively large, over 130 gram signals, so an entirely different form factor. The Mark 141 submarine smoke and illumination signal, we have, once again, it's a two-part parachute, and we have green smoke being used for daytime use and flare for nighttime use. This is the system is in a torpedo casing. It's launched from a submarine. It comes up to the surface and it expends these two smoke and flare candles, and they parachute down, as you can see on the right, you see the green smoke and the flare is closer to the ground. They're coming down in a parachute. You can see that the target, once again, it's not specifications, but our target is significantly different than that of the handheld signals. And our major accomplishments is that we identified our successful formulation based on our tunable green formulation that we have developed here at Crane. And formulation qualification is ongoing. This is a project that we are currently working on right now, and that formulation qualification is in process. We did a limited systems demonstration, which I'll talk about in the next slide. The systems demonstration, we tested various formulations. We varied fuel oxidizer ratios to show that we can change the burn time and intensity. And if you look at what the intensity target was and what we were able to achieve, you can see that we surpassed both what we were shooting for in intensity as well as burn time while producing a high color purity green light. We originally evaluated copper and boron for green color emitters in this form factor, but barium nitrate ended up being the best performing green emitter, as the other compositions did not meet that requirement. So our limited systems demonstration, we weren't able to do a full systems demonstration as discussed on the previous projects, but we did have 10 units made by the Crane Army Ammunition Activity. So we implemented this manufacturing procedure into a third full-scale manufacturing facility being located here in Crane, Indiana. And we were very grateful that the program office donated the parts, as these are very expensive signals to test. So we performed static pressure and function testing. We pressurized these units to real pressures that would be seen in service, and then we would flood a battery, launch these. The flare and the smoke would come out, and then we would be able to measure them in real life. You can once again see that our all the photometric performance requirements. We had superior performance versus the perchlorate-containing signals, there's no impact on signal function. And we once again demonstrated our manufacturability at a different full-scale manufacturing facility, which we're very proud of. The Mark 140, this is identical to the Mark 141 that I previously discussed. This is once again a submarine smoke and illumination signal, except now it's red instead of green. We're very proud of this one as well. We took the Mark 140 and 141 form factor, which is identical, and we simply what we call dropped in the Mark 124 composition. So we took the already qualified and characterized Mark 124 composition, and we simply put that into this candle, and we exceeded all requirements that are specified for this, that are targeted for this, this unit. So you have greatly superior intensity and burn time to the previous formulation and what we need for this unit. So you can see that we surpassed the intensity and burn time by not just a little bit. So there's a great deal of trade space there, and we have a lot of color purity and a very nice red color, dominant wavelength. The last unit I'm going to talk about is the smallest form factor, being the pin flares. These are under sub 5 gram units. They're about as small as a pen cap, as we call them, pin flares. And they are hand-fired visible distress flares, usually used by downed airmen. So the targets here are once again quite different than everything else we've done. We see about a 13,000 integrated candela seconds, so that's the integrated intensity requirement, and a 7-second burn time, so significantly shorter burn time than all of the rest of the units that we've discussed. This is also a current project that's ongoing, and some of the interesting work about this is that we've run into some very unique obstacles from the small form factor that we haven't seen in any of the larger form factors. So due to the very small size, we have seen some very irregular burning that we haven't really anticipated. If you look on the picture on the bottom left, we see a regular burning flare. You see a nice flame coming out of the small housing. But if you look on the right, you can see that top opening in the housing is obstructed, or in some cases we'll see that it actually burns through the side of the casing. And it's caused some very irregular burning, which results in a very wide variety of performance that sometimes can not meet our target performance specifications. So we still have our tunable formulation. This work is ongoing to try to limit this irregular burning. But it brings up some very interesting comments that we really have to have a good formulation to start with, and then if you put it in a different form factor, the performance is going to be entirely different. You're going to have to tune it to meet the specific application requirements. So that kind of wraps up all the different unit-specific conversation I'd like to have. I'd like to kind of finalize by talking about some future regulations. Considering all of our work up to this point has been motivated by the perchlorate regulations that are coming out, there's a lot of heavy metal compounds that potentially could be regulated in the future. We've seen a lot of regulations in the past on lead, and several of these ones that I've listed here. And future regulations on things like strontium or barium could be very difficult to deal with in the colored flare industry. Recently, in 2014, a preliminary determination from the EPA on strontium in drinking water was determined, so they're identified that as an area that they want to look into. Relatively speaking, strontium combustion products have relatively low water solubility, but generally speaking, if strontium and barium type compositions need to be reformulated because due to any future regulations, there'll be a considerable amount of work that has yet to be done. So these are all things that are identified as potential areas of interest by the EPA. And for a green formulation, if we can't use barium, then we're stuck with boron. And boron can be difficult to work with. It has relatively low combustion efficiency without getting too much into it, and it can be difficult to use. I'd like to call out that boron carbide research at the U.S. Army RDEC has been very successful, and they're putting out a lot of publications with various perchlorate-free formulations that utilize boron carbide as a pyrotechnic fuel. And they've shown acceptable performance specifically in the M195 form factor as well as in several other applications. If we can't use strontium, however, we're pretty much stuck with lithium, which has a significantly lower photopic efficiency. It's not going to be as brilliant of a red light as strontium-based is. Strontium is very good at producing red light, which will lead, there's not been a whole lot of work that's been done on lithium-based red emitters that I'm aware of. So I'd like to summarize by saying we've developed a series of perchlorate-free formulations that have been done collaboratively between RDEC and NSWC Crane. A variety of colors have been used. You see red, white, green, yellow, and a variety of signals. Some, the M126 is currently being used in service, and others have gone through systems demonstration, undergoing system demonstration, and some are still undergoing development. So there's still a lot of work to be done. We're very happy to be working on this type of work and hope to transition these items into service as soon as possible. I'd like to call it several contributors. This has been a long effort between us and RDEC. Dr. Robert Shortridge here at Crane was the original PI in these projects. He's no longer working here. He's retired. We see a list of other main contributors here, including Dr. David Dye and Christina Yamamoto, who's sitting in the office with me, and a long list of people. This has been a very extensive effort, as well as we'd like to thank RDEC once again for all of their collaborations. So I'd like to open it up for questions at this point.
Thanks, Eric, for a very informative and comprehensive presentation. We're going to start with one general question and then move into some more specific questions. We have received a few questions from the audience, and I would like to remind our audience at this time to submit questions for Eric by using the chat box in the lower left-hand portion of your screen. So the first just general question in response to your presentation, would you discuss the importance of color and burn duration for the smokes and flares? What is the importance of those two?
Yeah. The quality of the color is specified and has to be readily identifiable by their intended end users. So those are all identified and characterized and called out for specifically on a unit-by-unit basis. And once again, that color and the burn time is been determined and specified so that the unit is effective in its intended use.
Okay, thank you. And now some of the specific questions to specific slides. The first question is about the process you described as a partial cure process. How reproducible is it? And did you follow that partial cure process using any spectroscopic techniques?
It's very reproducible, and our candles were, the color output was found to also be very reproducible as well. I don't know if that exactly answers what the question is.
And the second part of the question was whether you use spectroscopic techniques to follow that.
Yes. The color is documented using a spectroscopic technique, and that was found to be very repeatable. Okay. All those techniques are standardized in the CIE color diagram. Those are all standardized. You can use several different instruments, and they will all give you very repeatable data.
Okay, great. And then talking about the color, there was a question about potentially using synthetic dyes. Have synthetic dyes been used for these purposes, such as red and yellow acid, or have solvent dyes been used for these purposes?
Yeah, one of my coworkers would like to jump in and answer this question, Dr. David Dye.
To address the question of dyes, dyes are used fairly extensively in the smoke formulations, and Crane has done some of the work to reformulate the smoke formulations before. But in terms of specific color emitters, you want to produce photon output, and the dyes aren't necessarily appropriate for that. When they burn, they generally just produce black smoke if they get too hot. So for the smoke compositions, we have looked at a variety of different dyes, and we've actually gone with food grade red dyes for the new smoke formulations. But for red colored flares, the dyes won't produce a red color when they're burned.
Okay, thank you. And then we had one question from the audience. I believe it was on this slide, slide 33. The question is, why is there a need to place the composition in a cup? I believe that was talking about this Mark 140 item.
The need to hold it in a cup?
Yes. Uh-huh.
This is a N-burning unit, so we need to inhibit the burning, and so it only burns on one side, so you get the burn duration, and this is the form factor that fits inside this unit. So that cup has been specified, so to design a new cup from scratch would be extensive work. And most of these reformulation efforts, what we'd like to do is just replace the Pyrotechnic formulation and keep as many other things as similar as possible so as to minimize cost.
Okay, thank you. And then just a couple of, again, more general questions. Which of these many units that you talked about may have the biggest future impact on reducing perchlorate contamination? Are there certain items that are some large contributors to perchlorate contamination?
Well, is the Mark 124? Mm-hmm. Yeah, the Mark 124 is the most widespreadly used unit out there. It's used in Navy, Marines, and Coast Guard across all services. So this is a very widespread used item, and we think that this will probably have one of the larger impacts of the units that we've addressed as far as removing perchlorates from the in-service inventory.
The M126 is also widely used as well.
Yeah.
Probably the most.
Yes.
Okay. And just one final question before we move on to our second speaker. Could you talk a little bit about the mixing procedure that you described towards the beginning of your presentation? Is that the primary way of making the pyrotechnic compositions?
You want to go? No, that is not the only way to make pyrotechnics. There are a wide variety of different mixing techniques and procedures. There's also a lot of proprietary information that specific commercial industries will use to mix theirs. To name a few, I'm going to pass this to Ms. Christina Yamamoto, who has extensive experience in this.
As Eric talked about, we switched from a dry binder mix to a wet binder mix. Dry binders are more commonly known for some of these flare mixes, and there's several different methods to mix dry binders compositions. And then the wet binders there's several new methods coming out to mix those, so we can't get into the details of all of those either, just because of the government work for them. So David might be able to chime in.
Sure. For the wet mixing methods that we're using, the one that's shown right now is it's called a Hobart mixer. It's essentially just a big KitchenAid mixer that they use for making bread, and it handles these high viscosity materials fairly well. There are also Muller mixers that use a continuous flattening method that just kind of folds the material into each other to get a good blend. And we're starting to explore some resonant acoustic mixing technologies, but that's not online yet. But any type of mixing method that just blends everything together can be done. But the important part to note about this is a lot of those materials are still mixed by hand. Most of the flares are still a very hands-on process. So the wet binder mixing method here that desensitizes the comp towards ignition during the mixing process is a big step forward in terms of safety versus the dry binder methods. So we're very happy with that. So there are a bunch of different ways that we can do it.
Okay. Thanks for the answer to that question. And we'll move on to our second speaker now. Thank you, Eric, Christina, and others for the answers during this question and answer session. As I mentioned, after the second speaker, we will have some general questions and discussion for both speakers. So now I'd like to introduce our second speaker today, who's Dr. Jared Moretti. He has been the technical lead of numerous research and development programs and testing projects in the Pyrotechnics Technology and Prototyping Division at the U.S. Army RDEC. Much of his current work focuses on the development of environmentally benign chemical formulations for mission-critical Army pyrotechnic devices. He has filed 4 patent applications and he has published extensively in peer-reviewed scientific journals. Jared holds a doctoral degree in organic chemistry from the University of Pittsburgh. Jared?
Thank you for the introduction. This is Jared Moretti from ARDEC, located here at the Picatinny Arsenal in northwestern New Jersey. Today I'm here to give a technical update on an ESTCP project aimed to develop and demonstrate new perchlorate-free and barium-free incendiary compositions for insertion into 50 caliber incendiary projectiles. This work leverages a previous CERDIP project led by Dr. Trevor Griffiths over in the UK. The result of that effort was a new composition based on sodium nitrate. We have borrowed as much as we could from this previous CERDIP effort, and to date we have successfully demonstrated interesting performance with a related composition also based on a sodium-based oxidizer. So I'll start off with a brief overview of what I'll discuss today. First, I'll talk about the purpose of the 50 caliber projectiles, specifically how we focused on one Army and one Navy product, the factors that affect performance in the many bullet qualification tests, the current technologies that are available for incendiary mixtures in projectiles, and some real test data of our new perchlorate-free and barium-free composition in actual bullet hardware as it compares to the standard specification. And then lastly, I'll discuss the current status and the path forward. Interestingly, we have some bullet fabrication and testing ongoing this very week at the manufacturer, so ideally we can have some very new results in a very short amount of time. It's a very dynamic project. So as I mentioned, we focused on the Army's M8 armor-piercing incendiary round, which does not have a tracer. It's shown in the upper left screen. It has a silver tip. And the Mark 257 dim tracer round, it has a violet tip. Dim meaning that the tracer component, another pyrotechnic that's pressed into the posterior of the bullet, burns to produce an IR trail along its trajectory. This IR trail can only be seen using night vision goggles. And directly beneath those images, I have a cross-sectional diagram of the entire bullet. As you can probably expect, over at the left portion here, the bullet is initiated by the primer. The molten slag resulting from detonation of that primer lights the propellant bed here in the cartridge casing, which is responsible for the motion of the projectile. This is the projectile, the bullet component at the very end. This is what actually travels downrange. And I have an expanded view of that over here on the right. This is another cross-sectional diagram. The incendiary composition is pressed into the nose of the bullet shown here, between the copper bullet jacket and the stainless steel core. Unlike the flares that Dr. MacLeish and Ms. Yamamoto just talked about, this burns very differently. Those flares propagated by a conductive heat transfer mechanism. The incendiary comp here burns primarily by a convective heat transfer. When it strikes a target, it perforates the jacket, and after penetration, a stream of incandescent particles is released, and those can light fuel vapors. At the very end of the bullet, for the Mark 257 only, the tracer composition is loaded, and this behaves more similarly to the flares that have just been discussed. It propagates from end to end and requires an igniter. It's pressed at relatively high pressure. So, in summary, this tip of the bullet is the business end. This is what we're most concerned with because that contains the incendiary mixture. And also, please note that this drawing it's really more of a cartoon than anything else. It's not to scale. The space between the jacket and the core, it's probably closer than what I have depicted there. So again, we focused for this project only on the two projectiles, M8 and Mark 257. So as I mentioned, the role of these armor-piercing rounds is to penetrate armor and ignite any volatile vapors that might be beyond that armor. What I've shown on the screen here is a flash silhouette that results from a typical flash test done during lot assessment. Here the direction of fire is from right to left. It penetrates this oblique witness plate, and it's hung at about 20 degrees to the normal, and then it penetrates 3 successive plates held perpendicular to the line of fire. And as you can see, the majority of the flash is held between these two plates here and here. This result is a high score for that particular test. This is supposed to mimic the walls of a storage container or the walls of an armored vehicle. Ideally, you'd want the flash to fire exactly at that point. And as you can see, there's a sinusoidal shape to the flash. This is indicative of the axial rotations of the bullet as it's traveling through the underground firing tunnel. It's sinusoidal because the puncture in the nose of the bullet is only facing the camera at certain times. So as I mentioned on my last slide, this device it's a metal plate, a conical metal plate backed by an explosive, and it's meant to direct energy from that ignition event toward a point, and for that reason, it's very reminiscent of a shaped charge. I'd like to think it's a miniaturized shaped charge. And as I talked about, it's ideal for penetrating armor and lighting the fuel vapors inside, but also a very important function is for marking location. We get a lot of feedback from users, from discussions we've had at our manufacturer, that the visible signature that is emitted upon impact with the target is visible from over 600 yards away, and so it's a convenient location marker, target marker. Now that I've discussed the purpose of the item, I'll get into more detail about the incendiary mix that's packed into the tube. It's typically comprised of a powdered metallic fuel. It has to be very fine. It's well known in pyrotechnics that the finer the particle size, the more intense and quicker the burn. And for the purpose of an incendiary flash like this, the event has to have passed in about 20 milliseconds or so. And so we typically use something that's about 200 mesh, less than 200 mesh. And that corresponds to about 75 micron on the US system. We typically use, the current incendiary mix uses a 1-to-1 chemical alloy of magnesium and aluminum. It's very useful for resistance to aging mechanisms. And that is typically paired in a dry fashion with a simple inorganic commercially available oxidizer. It's done to reduce the unit cost of the item, to simplify manufacturing, and ideally the oxidizer will be as non-hygroscopic as possible. One of the reasons that we did not proceed with the exact sodium nitrate composition developed by Dr. Griffiths was because of the hygroscopicity concerns expressed by the manufacturer. Our industrial manufacturing partner is located in the southern U.S., and it gets very humid during summer. And sodium nitrate on storage for years would not be amenable to production. And then lastly, the requirement for the incendiary comp is a very high enthalpy of combustion, typically about 2,000 calories per gram. Note that we're using less than a gram of composition in each bullet. Now that I've discussed the material requirements of a composition, I need to explain how the rounds are made in general terms, because as I'll show later, the manufacturing parameters can have a drastic effect on bullet performance. So first, the current spec, the Incendiary Mix 28, that's what's currently in production. It's loaded into jackets that have been fed into the powder feeding bay. It's done with a spoon, and the charge jackets are then carried along an assembly line to the next station where the stainless steel core is seated into the charge composition. And this can be shown with this this final assembly here. This is known as the second assembly process. Again, this is a cartoon. It's not drawn to scale. I really just wanted to show the importance of the delicate balance that must exist between seating of the core and the void space in the tip of the bullet, and this will be important for understanding the correlation between manufacturing parameters and performance. Now when you look at this, you'll notice that we are taking highly sensitive, finely powdered energetic material that's very prone to emission with little stimulus, and we are squeezing it between two metal parts. And you'd think that that is asking for trouble, particularly accidental ignition. These events are typically referred to as pop-offs at the manufacturer, and they do happen. They have happened in our demonstration. This was a major safety hazard, and it nearly shut down our demonstration. But thankfully, we seem to have identified the source of the problem, and our show was allowed to go on with our manufacturing partner. So once second assembly is complete, the assembled items are polished and fitted with a brass cartridge that contains the propellanted primer, and then subjected to a quality control process. Typically, the finished rounds are loaded into a carousel, weighed and measured, and if there are any rejects from that first pass, a second pass is allowed. Any failures beyond the second pass, and the round is discarded. Just clear this arrow. Okay, now that you know how the bullets are made, let me tell you about how they are tested. Very briefly, there are a total of 8 performance tests. They're listed in the left column. The data requirements, the document is in the middle, and the pass-fail criteria are on the right. Basically, the first 2 rows are the only things that affect the incendiary mix affects only those first 2 tests, incendiary flash and penetration. But it's not just as simple as optimizing the results on each test independently. As I'll explain in a second, the factors that affect each test are mutually interdependent, and so making a change that will help one typically hurts the other, and vice versa. There's a negative correlation between these tests. The third test, accuracy, you might argue that if you change the weight of composition that you load into the bullet, that will make it a little more top-heavy. It might affect the ballistic performance. But do realize the round itself weighs quite a lot, well over 100 grams. And any change to the typical production weight of the incendiary comp would only be 10 or 20 milligrams. I don't have the results in this presentation, but we have done accuracy tests, and we have been able to meet the requirement without a problem. The remaining 5 tests you have listed there, that is mainly related to the propellant and the primer. And so swapping one incendiary mix for the other should not be effective, should not affect any of these tests. So in summary, it's just the first 2 tests that need to be balanced, striking the right balance between the chemistry in the bullet tip and the assembly of the 2 metal parts around it. Okay, more on those 2 tests. First is incendiary flash. This is a reproduction of the image that I showed earlier. Essentially, it's an indoor tunnel, and the testing area is divided into different zones by aluminum alloy sheets. Bear with me. Now, the direction of fire is from right to left. First, it breaks through this oblique witness plate. It's, I believe, 20 degrees to the normal. And then it passes through a series of 3 different perpendicular plates. Ideally, the combustion of the incendiary mix will follow a timed release. You want it to go off between here and here, as I alluded to earlier. This is the Zone 2 sweet spot. This will result in a score of 100% on the incendiary flash test. This is very much the ideal. We typically have some flashes that bleed into zone 3 or bleed into zone 1. Zone 1 is premature ignition. Zone 3 is immature ignition. I can discuss later on how the changes that you make in assembly can shift the timing of the flash to zone 1 or zone 3. But essentially, the way this test is scored, for each round that is tested, a digital photo like this is generated using a high-speed camera. I'm not sure of the triggering mechanism, but the resulting image is compared to a set of standard images across 5 categories, from 5 through 0, 5 being a very high score, all in zone 2, to a 0, which is no flash at all. The intermediate scores, it's typically for any flashes that bleed into the other 2 zones, and typically lower scores are issued for those. So again, for a typical lot assessment, you would only test 20 rounds of a lot of say 1,000 or 10,000. That's the flash test. On to the penetration test. It's a lot less subjective than the incendiary flash test. Again, you're using an underground tunnel and firing at a plate, but now the plate is a lot thicker. It's about a 1-inch stainless steel plate. The tunnel is 100 yards long. Again, 20 rounds are assessed per lot, but there's really only one outcome that is acceptable, and that is complete perforation. And I have that boxed off on the left in green. All other outcomes, I've listed 2 of the possibilities there in the red box. Those are not credited. What you're really looking for in this test is that the core has penetrated through the jacket and punched out a clean hole in that 1-inch plate. Anything else, the core piling up in the plate and or partial penetration, that is not scored. You get a score of 0 for that. Also importantly, the performance of the incendiary mixture has almost nothing to do with passing this test. In the past, inert salts have been loaded into the bullet tip, and the result has been very favorable. It's not related to the energetic content like the flash test is. The flash is very, very clearly related to combustion and emission of incandescent species, incandescent combustion products. So now that you know about building bullets and testing them, I'll tell you the problem that we currently have with the production item. The armor-piercing incendiary rounds are charged with about 12 grains of incendiary mix 28, and I've detailed that here on the slide. It's a 4:1 to 5 ratio of barium nitrate to potassium perchlorate to 1:1 magnesium aluminum alloy. The combustion product of barium nitrate is barium oxide, which is a powerful gray body emitter. Similarly, that of magnesium and aluminum is the corresponding oxides, which are also pretty powerful gray body emitters. The gray body emission is responsible for the flash. But the problem is, as Dr. MacLeish mentioned in the previous portion of the webinar, potassium perchlorate is a huge problem. There's a big push in the military to eliminate it from weapon platforms. And similarly, barium is a heavy metal. It is not currently, to the best of my knowledge, it is not currently regulated material, but it has been cited as being a bad actor from an environmental and freight and transport standpoint. So it's in the best interest of the military to remove that from the armor-piercing incendiary rounds. That said, any new composition should exclude potassium perchlorate and any heavy metals. Dr. MacLeish also mentioned previously of the very recent strontium regulation that has been passed as late as October 2014. Strontium is a very near neighbor to barium, and barium may be the next shoe to drop. And so when designing a new composition, it's best to exclude that as well. And while we're at that, we need to comply with the hygroscopicity limitations at the manufacturer. And so something like sodium and potassium nitrate are also not very helpful. Dr. Griffiths in his final report for the CERTA project has discussed a lot of aging protocols and some very elegant bullet prototyping tests, and I've included a link to that at the bottom. There's a lot of environmental discussion on said ingredients, and I won't recapitulate that here. So that brings us to our technology demonstration project. Initially, there was we have a three-way teaming a partnership between us at Ardec, the Pyro Group, Christina, David Dye, and Eric MacLeish over at Crane, as well as our industrial manufacturing partner, now ATK Orbital. We initially demonstrated two compositions, one based on strontium nitrate as the principal oxidizer, and the other with sodium metaperiodate or sodium periodate as the oxidizer. We kept the fuel the same, that is 1-to-1 magnesium aluminum alloy. We developed and tested some different compositions with different stoichiometries in each of those binary mixtures, strontium nitrate magnesium and sodium periodate magnesium. We made our down selection decision before the October 2014 strontium regulation, but the new regulation added weight to our decision to choose the sodium periodate composition. Our down selection criterion was solely on performance. The periodate compositions slightly outperformed it, and so choosing it was a logical step. There are some other benefits conferred by this oxidizer. For a sodium compound, it is very non-hygroscopic. You can buy it in bulk from many different distributors, and so it's a cost-effective alternative. And lastly, it's officially free of any bad actors. We've been assured by the U.S. Army Public Health Command that there are no chronic toxicity issues associated with the compound. There is some slight acute toxicity, but that's probably due to the basicity of the periodate anion in the stomach. But it's been characterized as having a chronic toxicity in the range of TNT, and so it shouldn't be a showstopper from inclusion in any weapon systems. So in summary, the result of the first 5 builds of this demonstration project was to choose this composition shown in the table. It's a 40-60 mixture of periodate to magnesium, and the magnesium is in accordance with the spec I've just shown. That's a U.S. standard. Oh, I advanced. Okay. So now that you know about our new incendiary technology, let me tell you about the lessons that we've learned along the way over the last 13 or 14 builds at the manufacturer. How to get good performance in the full-up system hardware for our new composition. We've learned that, referencing this drawing, this cartoon that I have on the right, striking the right balance between the flash and penetration tests is very delicate. You need to seat the core at an appropriate level so that the mix inside is adequately compressed, but you also don't want it to be seated too deeply so as to eliminate the void space in the tip of that bullet. When I say void space, I mean the empty space between the mixed particles themselves and between the mix and the metal parts. Because this is a convective heat propagation, heat transfer, timely propagation is directly related to having enough space for the gases resulting from combustion to effuse through the deformed material upon impact. And so, that said, there are 2 key manufacturing parameters, and that is core depth, as I alluded to earlier, seating it to an appropriate extent, and then charge weight. You need to load the tip with enough, of course, to produce a flash, but also enough to accommodate that open space. And more on that later. But also the physical properties of the mix itself. As long as it meets the combustion enthalpy requirement, which is pretty loose, there should be enough energy in the mix to deliver an adequate flash. but also particle size of the oxidizer, flow agent that is added to the mixture. That'll affect the pourability and the bulk density of the overall mix. And throughout our demonstration, we've used hydrophobic untreated fumed silica and calcium stearate as a flow agent. So the first thing that I discussed, it's a manufacturing parameter, core depth. Again, referencing the cartoon drawn on the right, during assembly, the core is placed inside the jacket and then punched downward, sort of pressed. It's not at very high pressure. It's a measure of how deeply seated, how far the core is seated into the bullet jacket. And the lower the number, the more deeply seated it is. A typical benchmark for the production item is 90,000ths of an inch. To put that into perspective, a human hair is roughly 3,000ths of an inch. I'm not entirely sure, to be honest, I'm not entirely sure of what that distance is, but I suspect that it's the distance from the tip of this core to the inner tip of the jacket. And this really is critical. If it's seated too deeply, then you'll compress the mixture, and too much, and there won't be enough void space between the particles to have successful flash. It won't burn fast enough in that to reach that, for most of it to be in that zone 2 sweet spot. It'll go out to zone 3, if at all. If it's not seated deeply enough and it's not making intimate contact with the mix, then too much kinetic energy will be dissipated from the core sliding down into the bullet, and the mix will behave very much like a pillow, and then you'll fail the penetration test. So this is part of the mutual interdependence that I mentioned earlier. You'll get failures if it's not in the right spot. That said, charge weight is another parameter for variation. And this is more critical to the flash test. Again, you need the right balance between void space and energetic content to do well in that test. You need open space for the gases to flow. And the chart that I have on this slide nicely demonstrates the interdependence that I mentioned earlier. The top row is a build of bullets based on IM-28. And as you can expect, we got very high scores in the high 90s and 100% when the typical methods are implemented. The next 3 rows are for the sodium periodate composition, and it demonstrates the nice trade-off between flash and penetration that exists. Over in the charge weight column, we have 3 ranges of charge weight. They're ranges because they're done by quality check. I can explain that in the Q&A session if you need. But essentially, the charge weight is increasing going down this series while the core depth is held the same pretty much. The first row represents a lower process boundary. That's where you don't have a good balance between flash and penetration. You have excellent flash, but unacceptable penetration. The next one, you seem to have struck that right balance. You have just enough material in there at exactly the right core depth to give nice high scores on both tests. But then when you raise it further, charging becomes erratic, and at higher charge weight, you seem to have identified an upper process boundary. And you can see also that the core depth has drifted north of that 90,000th of an inch benchmark. And this is intuitively obvious. If you add too much material, you're not going to be able to push that core down as far. The mix is in the way. So with that said, when you take a look at the second row of the sodium periodate performance composition, it looks like you've identified a set of conditions where you have nice high scores on both tests. So clearly you have the problem solved, right? Wrong. Later builds showed that Arriving at those manufacturing parameters, charge weight and core depth was not as reproducible, and that was mainly because we were using coarse granular sodium pyridate from a distributor. And as you can see on this table, the charge weight ranges are very broad. It's like 100 milligrams almost in both cases. And for production, we wanted to target something closer to IM28, which is usually 40 or 50 milligrams. Also, our core depth ranges were more variable. And for consistency purposes, we thought it best to use some finer sodium pyridate. When we do that, you can see we were able to identify a stable charge weight range and core depth range, and we restored our flash and penetration performance. But this leads into my next point, the flow agent that we used. It's untreated fumed silica available from Cabot Corp under the trade name Cabosil. We chose the level of that content to be a 0.25%. Now, this was based on our previous experience with other pyrotechnics like flashbang simulators where the composition is loaded as a loose powder and not pressed. We found in that project for consistency purposes to use that level or something close to it, between 0.25% and 0.5% to be ideal. We would later find out that this might actually be too high, but I'll discuss more on that later. So again, 0.25% Cabosil. It's a flow agent. It is great in very low loadings to improve processing. It behaves like a binder, and so it can modify burn rate. Again, the timed release is essential to flash success. And also it can modify sensitivity by coating the particles and covering up any jagged edges or surfaces. We found that a little bit of flow agent was essential because without it, the flash test, I don't have the results shown here, but the flash test gave some very bad pre-ignition flash silhouettes in that zone 1 region, right after the oblique plate and just before the first perpendicular plate. And one thing that we needed to keep in mind was that IM28, it's not normally used in production. I'm sorry, Cabosil is not normally used for production of IM28 at ATK orbital. It's listed as an optional 0.02 weight percent. That's right, you saw it, 0.02 of a weight percent, which seems very low based on our experience, but more on why I think it is that way later. Continuing with the composition based on fine sodium pyridate and Cabosil led to those incidents that I talked about earlier, the accidental ignition known as pop-offs, and that led us to a temporary shutdown of demonstration. We had to convince the safety board at ATK that we understood why they happened and measures that we could put in place to prevent it from ever happening again. Our first instinct was to blame the metal hardware. Maybe there was a jagged surface somewhere. Maybe something was out of spec, but they assured us that that was not the case. And so analysis of the sodium pyridate sample that we had led us to believe that the fine granules led to the pop-off incident. Fine granules are pretty notorious for leading to increased sensitivity. You have more surface area, and in an environment like this where you're literally squeezing it between two metal parts, it's reasonable to hypothesize that. And so to test that, we wanted to conduct some additional builds. This time with 2 batches of the sodium pyridate composition. One based on oxidizer that has been unscreened as before, and the other where the fine particles have been screened out. Use these 2 batches to build M8 and Mark 257 batches. And a further wrinkle was for us to control the charge weight. I have 4 very narrow and almost overlapping charge weights. This was done by hand. We didn't even use machine loading, just to eliminate charge weight as another possible failure mode and as another possible cause for the pop-offs. Now what we've shown over in the chart here, F stands for fine. We only made 2 lots of those in the M8 platform, and then the 4 at the 4 charge weights listed on the left. Sure enough, there were no pop-offs observed during this time. It was only when we made Mark 257 rounds that we observed 2 pop-offs within the first 8 Mark 257 bullets made. That's right, 2 of the 8 went, and that was using material based on, that didn't have any fine particles. So clearly that hypothesis was wrong. But also interestingly, this is some of the best performance that we had ever seen for this composition. So that led us to our current hypothesis, that the failures were not caused by the fine particles there. Now we believe that it was the silica that was to blame. The content of the Cabosil was at too high a level. Silica, as you might expect, it's much like ground glass. It's less than 10 micron material. And so you're creating too many pinch points within other oxidizer granules that are already very fine. And so sensitivity may have spiked due to that. And that also may explain why the IM28 composition recommends only 0.02 weight percent silica. So our initial instinct was to change the flow agent, just switch from Cabosil to something like calcium stearate. Without changing the loading. Again, we tried 1/4%, 1/4 of 1 weight percent in our build, and sure enough, we didn't observe any pop-offs. We were able to handle it safely, even in the machine. But the problem was that it acted as a lubricant, and it contracted the volume so much. It enhanced the bulk density way too much. We were unable to seat the core as well, and it resulted in a complete knockout of penetration performance, as shown in the table on the right. They're all red for the bullet lots that contained our control composition. We had acceptable or somewhat acceptable flash, not as good as before, but it detrimentally affected our performance. So now this week's build is I don't have it shown, but we've reduced the loading. We're building 2 lots of bullets, or rather 4 lots of bullets, 2 M8s and 2 Mark 257s. And for each bullet platform, we're making 1 lot based on 0.05 weight percent Cabosil and 0.05 weight percent calcium stearate, and the same for the Mark 257 lots. And we can already see that just by blending the lots that there is a significant difference in bulk density. But we think that we can regain that performance while handling it safely inside the machines, and from there we can continue with our demonstration project. So in summary, we've identified a robust new system based on a powerful sodium-based oxidizer. Sodium is very valuable as an oxidizer for producing visible light. So the atomic emissions associated with that atom are very high at 589 nanometers, and so it can offset any loss from removing barium nitrate from the composition. We are currently working the flow agent challenge. This week we are examining Cabosil and calcium stearate systems under modified conditions. And then once we have this last wrinkle ironed out, we can go into production of larger lot sizes, like 1,000 rounds for each the M8 and Mark 257 platforms, using our new alternate incendiary mix. And then lastly, once we have that done, we might be able to spin this technology off to another Army product, the M20. That is like the M8, only it does have a tracer. It has a red visible signature upon burning and firing. But that will have to wait for now. There is no current plan to include that in this demonstration just yet. Perhaps if we can fix this problem fix this challenge very soon, which I think we will, we can approach sponsor for more support. So lastly, the key to replacing the incendiary mix in 50 cal incendiary bullets is to strike the right balance between flash and penetration performance. And that can be done by tuning the intrinsic chemistry of the mix, the particle size and physical properties of it, but also by the machine settings. And the benefits of this work will be that the soldiers will maintain capability with no disturbance in their training schedules or combat operations, and the environment will also benefit. There will be a clear and obvious benefit to humanity once a new greener round is implemented. And with all that said, I'd be happy to answer any questions that you might have.
Thanks, Jared. We do have a few questions from the audience. We'll give one or two specific ones to you and then bring Eric back as well for some additional questions.
Okay.
First for you, Jared, is have you performed any hazard testing of the new formulation, and how does it compare with the typical pyrotechnic formulations?
We have done substantial sensitivity testing on our composition across a range of particle size, across a range of oxidizer particle sizes. As you might expect, being an incendiary composition, it's much like a flash powder. It doesn't get a lot more sensitive than that. I would say it's in the same family as the existing mix. It's nothing nothing extraordinary. It's just that with our particular mix, pop-offs resulted because of being in the wrong place at the wrong time, so to speak. And I believe it will be fixed by simply reducing the carboxyl content.
Okay, great. And can the perchlorate-free incendiary composition affect the use of APIs for low-order detonation purposes?
Can you repeat that, please?
The question is about the composition. Does it affect the use of API for low-order detonation purposes? And the questioner mentioned EOD, SMUD.
Can affect the use of API for low-order detonation. Well, I'm not really sure I understand what's being asked. The composition itself, on impact, it really doesn't detonate. The use of the 50 count for low order. I guess, are they talking about I guess they're talking about the target. When it strikes a target, that might detonate. I don't think that there will be any loss of performance for the new perchlorate-free incendiary composition. I'm confident that it has enough energy to do its job and have a devastating effect on any fuel-containing structures or vehicles. And it will. What's interesting about this new composition, it's based on sodium, a sodium oxidizer, and that gives a nice bright yellow flash upon impact. For the current IM-28 baseline, it's a very dim blue. So we might actually have an advantage for marking location because the gunner can probably see it from further away, a lot further than 600 yards. Okay.
And if we could bring Eric back on the line, we have a question that is for both speakers, and it's about the aging of the formulations. Have there been any aging studies performed on the new formulations? Have you seen any interesting aging effects, if so? So Eric, would you answer the question first?
Yes, gladly. Part of the formulation qualification process, which is done very early on in these studies, is doing an aging study, and we have all of our compositions that we've discussed today have shown no significant decrease in performance with aging. So this is all done according to military procedures for these types of formulations, and there was no significant effect on anything from aging.
Okay, Jared.
For our composition, we haven't done any. We haven't done any aging tests just yet. That's usually part of standard energetic material qualification. But I do have previous experience with the compound, and there is no real issues with caking over time, over the course of years that I've experienced, at least with the oxidizer, and that's often a problem with loose powder mixtures like this.
Mm-hmm. All right, and with that, that brings us to the end of our time for the webinar. I'd like to thank both of our speakers for the excellent and informative presentations and answering so many questions from the audience. The next webinar in the CERDP and ESPCP webinar series is on August 20th. It's on characterization and remediation in fractured rock environments. And I would like to remind the audience to please take a moment to complete the survey. It will pop up on your screen when the webinar ends, and that helps us to continually improve the webinar series. This concludes today's webcast. Thank you.